Now here's a deformation that can actually be measured, and it's called Hooke's law, and it has to do with something known as the spring constant. Hooke's law is the mathematical calculation of deformation when the deformation is small. Force is equal to a constant times the amount of deformation x, where x would be along the x-axis. So here we have an example of that. And what you have here, you start out with a spring that's at a particular baseline level here. If this spring moves a distance of x because of a force caused by this weight here, then this moves a distance of 2x when you have 2 times the force applied. And so x is related to this force F by a constant known as the spring constant. So now let's look at this and look at some problems that can be done using this concept. What is the force necessary to stretch an ideal spring whose force constant is 120 newtons per meter by the amount of 30 centimeters? So if we look at how we would approach a problem like this, first of all, we have a spring whose spring constant is 120 newtons per meter. So that means that K is equal to 120 newtons per meter. And the distance is 30 centimeters, or since this is in meters, let's change this to meters, which would be 0.3 meters. So we have our formula, which was F is equal to Kx. So F is going to be 120 times 0.3, or 0.36 newtons. I'm sorry, that 36.0 newtons. Actually, they don't need this 0.0. It'd just be 36 newtons. 3 times 12 is 36 newtons. Now the second problem here is the spring is compressed 12 centimeters, so x here is going to be 0.12 meters, or 12 centimeters. And it's a 40 kilogram girl. So m, her mass, is equal to 40 kilograms. Now I'm just going to have to tell you that to convert her mass to a force, you have to multiply by gravity. So that's going to be 40 times 9.8, which is gravity. And so you have, that's going to equal 32, 3 is 392 newtons. Okay? And actually it'd be 390 with the significant figures. And so we have F is equal to 390 newtons. And X is equal to this. And the question is, what is the force constant? And so again, F is equal to Kx. And so K is going to be F divided by X, or 390. We'll go ahead and put the 2 in, and we'll use the significant figures at the end, divided by 0.12 meters. What comes out of the calculator here is 3,266.6666, and we round up, so we drop all of this junk and just say 3,300 newtons per meter, and that's to 2 significant figures. I decided to move this to 392 and do the significant figure calculation at the end, which is probably the best way to do it. So the answer here is 3,300 newtons. Now let's take a look at the properties of liquids. The first of these properties is something known as adhesion. You'll remember we talked about cohesion being the attraction between molecules of the same type. Adhesion is the attraction of molecules that are of different types. Surface tension is a film of force on the surface of liquid that's due to an imbalance of these cohesive forces. The forces on the surface versus the forces underneath the surface of the liquid. Capillarity is when liquids will travel up a thin tube and rise inside that tube due to both cohesive and adhesive forces. If the adhesive force is greater than the cohesive force, the liquid will actually travel up the tube. Conversely, if the cohesive force is greater than the adhesive force, it will actually be pressed down inside the tube. A meniscus is what happens when the liquid rises on the sides due to the adhesive force and it's greater than the cohesive force of the liquid. You'll remember when I talked to you about how to measure the level of a liquid inside a graduated cylinder, you always read the bottom of the meniscus. Now, another concept of liquids, and also gases for that matter, is the concept of pressure. Pressure is the force exerted by a substance over an area of which the force is exerted. So force per unit area. So pressure is equal to the force divided by the area. The most common, the System International unit for pressure is called the Pascal, and a Pascal is the number of newtons divided by the area in square meters. So, for example, in the case here on the left, this cone of material, solid, pushing on this square will exert a certain force, and it will be over the area of that cone or that cylinder. And so the pressure would be the total force divided by whatever the area of that circle is. Now here you see an example of a difference in pressure. The force is exerted by the thumb. The pressure on the thumb is far less than the pressure on the wood. Although the force at both places is the same, the area is different, and so the pressure is different. And therefore, the nail does not go into the thumb, but goes into the wood. Gravitational pressure is the pressure that occurs due to the weight of the liquid. The force of the liquid is the weight, and then that weight is distributed over some area, so gravitational pressure represents the weight of that liquid over the area that the liquid's contained in. It's generally felt in all directions at any given point. It's affected by the depth of the liquid, the density of the liquid. So let's look at a couple problems taking into account pressure. A pool measuring 50 by 25 by 4 is filled to the top with water. If the density of the water is given here, what is the pressure on the bottom? Okay, let's take a look at how we would do this. First of all, remember that pressure is equal to force divided by area. Okay, so how much force, or what is the weight of this fluid in this pool? Well, it's going to be the volume in the pool times the density. Because remember, density is the weight divided by the volume. So if you know the volume and you know the density, then you know the weight. So the force is going to equal the density, rho, times the volume, which is going to equal, in this case, 9799.706 times, and then the volume here is going to be 50 times 25 times 4. So this is going to be 100, 4 times 25 is 100 times 50 is 5,000. So it's going to be 5,000 times this, or you take the 3 zeros and move your decimal over this way. So 5 times 6 is 30. 5 times this is 35. Carry 3 over here. 5 times that's 45 plus 3 is 48. 5 times that's 45 plus 4 is 49. 5 times that's 35 with 4 is 39 again. And then 5 times that's 45 with 3 is 48. And so the total weight here is going to be 48 million and some change, almost 49 million newtons. And then to calculate the pressure on the bottom, you take that force, and notice I haven't done significant figures yet because I haven't finished the calculation, and divide it by the area, which is not the height, but just the length times the width, which is 50 times 25, and 50 times 25 is going to be 0. 5 times 5 is this, 10 is 1250. So if we do the math, we get 39198.824 newtons per meter squared. And if we look here, this is 3 significant figures, 3, 2, and then this is like 7 significant figures. So all of this falls off and we round down to 33.9 times 10 to the 4th newtons per square meter or Pascal. So that's the pressure on the bottom of the pool there. Let's take a look at the second problem. The vertical tube with a radius of 1 centimeter. So it's a tube with a radius of 1 centimeter or 0.01 meters. Closed on the top to the atmosphere, contains 30 centimeters of mercury. So 30 centimeters or 3/10 of a meter of mercury. If the pressure, if P is equal to 4.00 times 10 to the 4th newtons per meter squared, what is the weight density of mercury? Okay, first of all, we have to calculate the area, and the area of a circle is pi r squared. So the area here is going to be 0.01 squared times pi. The area is going to equal 3.14159 times 10 to the minus 4 square meters. Okay, and we know the pressure is equal to force divided by area. So force is going to be pressure times area. So force is going to be 4 times 10 to the 4th times 3.14159 times 10 to the minus 4. So that's going to, so the force here is going to be 12.5637 newtons. So that's the force on the bottom. And that force, now we know that the force is equal to density times volume. And so density is going to equal force divided by volume. So that's going to equal 12.56637 divided by, And the volume is going to be the area times the height. So it's going to be 3.14159 times 10 to the minus 4 times 0.3. So the weight density is 13333.446 newtons per meter cubed. Now we have to simplify this, and so we can say, again, we go back over here and we see that we have 3 significant figures here, 3 here, and 3 here. So we need to round this to 3 significant figures. So let's put we're going to say it's 1.33 times 10 to the 5 newtons per meter cubed. Now remember, water was times 10 to the was almost 10,000. And so this is not outrageous when you consider that mercury is about 13 times as dense as water. So that's the weight density of mercury right there.